Good morning, students. Myself, Vaidehi, working as Assistant Professor in Sri Muthukumaran Institute of Technology. Today, the video lecture is from the subject EC 3452 Electromagnetic Fields for the 4th semester EC student. Today, the video lecture is from the Unit 4 Time Varying Fields and Maxwell Equations. The topics we are going to discuss is electromagnetic boundary conditions, wave equations and their solutions, and time harmonic fields. These concepts are fundamental for understanding electromagnetic wave propagation, antennas, wireless communication systems, microwave engineering, and optical communication. Next, we see about the introduction. Electromagnetic fields can either be static or time varying. When electric and magnetic fields vary with the time, they become coupled and generate electromagnetic waves. Maxwell equations provide a complete mathematical description of this phenomena. The study of time varying fields form the foundation of modern communication technologies, including radio, television, mobile networks, and satellite systems. Next, we see about the electromagnetic boundary conditions. Boundary conditions describe how electromagnetic fields behave when they encounter the interface between two different media. These conditions are derived directly from Maxwell equations. They help us determine how waves are reflected, transmitted, or refracted when moving from one material to another. Understanding boundary conditions is essential in designing antennas, waveguides, and transmission lines. Next, we see about the boundary conditions for electric fields. Let us consider the behavior of electric fields at the boundary between two media. The tangential component of the electric field remains continuous across the interface unless there is an infinite electric field across the source. The tangential component of the electric field remains continuous across the interface unless there is an infinite electric field source. The normal component of the electric flux density depends on the presence of surface charge density. The relationships are important when analyzing dielectric materials and capacitor structures. Next, we see about the boundary conditions for magnetic fields. For magnetic fields, the tangential component of the magnetic field intensity is influenced by any surface current density present at the boundary. The normal component of magnetic flux density remains continuous across the interface because magnetic monopoles do not exist. These boundary conditions are widely used in magnetic material analysis and electromagnetic device design. Next, we see about the wave equations. Wave equations are obtained by combining Maxwell's curl and equations. These equations describe how electric and magnetic fields propagate through space and material media. The solutions of these equations provide information about wave velocity, wavelength, frequency, and phase. Wave equations are central to the study of electromagnetic wave propagation. Next, we see about the wave equation in free space. In free space, electromagnetic waves propagate without requiring any physical medium. The electric and magnetic fields satisfy second order differential wave equations. The velocity of propagation is equal to the speed of light, approximately 300 million meters per second. The electric and magnetic fields are perpendicular to each other and to the direction of propagation, forming a transverse electromagnetic wave. Next, we see about the solutions of wave equations. The most common solution to the electromagnetic wave equation is the plane wave solution. In a plane wave, the electric and magnetic fields vary sinusoidally with both time and distance. The important parameters describing a wave include amplitude, frequency, wavelength, phase, and propagation constant. These solutions help us understand signal transmission through various media. Next, we see about the time harmonic fields. Many practical electromagnetic systems operate with sinusoidal sources. Such fields are known as time harmonic fields. Instead of solving Maxwell's equations directly in the time domain, we can analyze them using frequency domain techniques. Time harmonic analysis is greatly simplifies calculations and is widely used in communication and microwave engineering. Next, we see about the phasor representation. Phasors provide a convenient way to represent sinusoidally varying quantities. By using phasor notation, differential equations are converted into algebraic equations, making analysis much simpler. Phasor representation is extensively used in AC circuit analysis, transient line antennas, and magnetic field problems. It allows engineers to efficiently calculate voltage, current, and field quantities. Next, we see about the applications. The concepts covered in this unit have numerous practical applications. Waveguides and transmission lines are used to guide electromagnetic energy. Antennas enable wireless communication by transmitting and receiving electromagnetic waves. Microwave systems, radar technology, satellite communication, and optical fiber communication all rely on the principles of time varying electromagnetic fields and Maxwell equations. Finally, we came to the summary. To summarize, electromagnetic boundary conditions describe field behavior at material interfaces. Wave equations derived from Maxwell's equations explain how electromagnetic wave propagate. Time harmonic field analysis and phasor representation simplify complex electromagnetic calculations. Together, these concepts provide the theoretical foundation for modern communication and electromagnetic engineering systems. Thank you for your attention. In the next lecture, we will continue exploring advanced applications of electromagnetic wave propagation and field analysis. Thank you.